So our second speaker today is Daniel Hansson from Cadence Design System, where he is Senior Principal Software Engineer. He's going to be talking on predicting bugs and validating bugs. So Daniel has 25 years of experience as an ASIC designer, project manager, and tool developer at Ericsson, Texas Instruments, ARC, now part of Synopsys, Verifyter and Cadence. Daniel has spent the last 10 plus years working on automatic debug and ML-based bug prediction with 2 patents granted in the field. Cadence is a senior for Vericym pin down, the automatic debugger of regression failures. Over to you, Daniel. Thank you.
Okay, thank you. Okay, so I'm going to talk about bug prediction. I actually talked about bug prediction 2 years ago. I'll also give you a little bit of up. 2 years ago were acquired by Cadence, and we're now part of their tool chain. Anyway, what is bug prediction? So the definition of that is to locate potential bugs without running any tests. So it's very fast. And we use machine learning to analyze data in the revision control system, like Git before Subversion, also Mercurial, and other data sources. We use these as features for our prediction. And the outcome is that all code changes, all commits to these revision control systems are risk classified. And the benefit is faster debug verification. So just starting with this picture, which is sort of the same starting picture that Rajesh showed, that there has been a number of commits historically. In this example here, we have Git. So each line here is a Git commit from different people. There's a failure here in this scenario, and which one of these commits have caused this failure? And debugging, it's one of the most time-consuming tasks. So any speed up here is welcome. Okay, so what we do with bug prediction is basically to sort this list in terms of risk. So we add a prediction value between 0 and 1 for each commit, and then we sort these recent commits in order of probability of containing bugs. And we have found out that in 50% of the cases, the bad commit is in one of the top 3 most risky commits. And that leads to faster debug, because if you only have to focus on the 50%, on the 3 commits which with 50% of chance contains the bug, then half of the time you can identify the bad commit immediately, very fast. So the whole idea with bug prediction is to be fast. The way we do bug prediction is we suck out features from the revision control systems, such as Git before, etc., and the code and logs, etc., but mainly revision control system and the code itself, and create features. And these features we use to identify bugs. And the reason we know which commits are good or bad is because Pinnan has generated a lot of data over the years running. So we have a lot of historical good, bad data preserved internally. So Pinnan actually comes with a pre-trained model which has used all that data. Okay, so now an example. So what do we use this for? So in the scenario where you have a failing revision now, and you had a passing revision before, then what Pinnan will do is start with doing this risk classification. And this risk classification is very quick. It reads the metrics from and create metrics from each commit, and this creates this ranking. But it's very fast. It's done before the test is passing. So in this example, commit 115 is the highest risk. So what Pindown then will try to do is to back out just 115, leaving everything in there, older and newer commits, recompiling and rerunning the test. And if the test now passes, then we say that this bug report has been validated. And validation is a key thing here when it comes to machine learning, not just in our scenario, but I think in all ML scenarios, you have to think about how do I validate my results, because machine learning is always going to be, at best a very good guess, but how do you separate the truth from the non-truth? There you need either a validation process, or you as a human need to do that decision whether this is relevant results or not. But with Pindown we have this automatic validation process where it basically continues until it has made the failing test pass again. In a little bit more complicated scenario, here we have results from the latest, which was failing, and before, as before, oldest was passing, and then we have some results on various revisions in between. And when you look at this data here, it certainly looks like 113 introduced a failure because 112 was passing. But because we don't run every single revision, we don't know if it's been fixed. And in this scenario, this bug in 113 has actually been fixed already in 114, but we don't know about that because we haven't run any test on 114. So what will happen in this scenario is that Pindown will validate by backing out just 113, but in this case it will fail. So now it knows that its original ML-based bug prediction was incorrect. And it could have been that the prediction was actually fantastic. It did contain a bug after all, but this bug has been fixed, so it's not the reason why this test is still failing. So then Pindown continues and will try instead to validate 115 in this scenario, and then that succeeds. So now Pindown has validated that it was 115 and not 113 that caused this test to fail, and then that bug report can be sent out. So the important thing here is that, as I said in the beginning, in 50% of the cases, one of the top 3 most risky commits actually contain the bug. And the way we know if which one of these 3 it is, or if it's something else, is by this validation process. So the ML ranking is very important to do the risk ranking, but then even more important is to validate all the good guesses coming out, so we can pick the winner and have a fast bug report also being correct. So I don't have many minutes left, but I want to show you just how this now hangs together, because now we have a solid validated result to rely on, and we've been part of Cadence now for a while, so now we can build a tool chain on that solid foundation. So if we look on in a regression environment, what we have here is, before Pindown, you have some regression tests being run nightly, and then you have some poor person manually debugging that regression failure and identify root cause, and it goes around like this. Now with Pindown and the other Cadence tools, we can automate this flow, and then we have various tools here like auto triage is doing the clustering, and then pin down is identifying and validating the bad commit quickly thanks to this ML thing. And then semantic diff takes the validated bug report and sends it to Wayminer, which then will analyze the difference between passing and failure. And because we have validated bug report, we have the good pass, we have the good failure, we have a solid foundation to build on this. So I'll just show 1 more minute my finishing slides, because they are animated, and animated slides, as you all know, are very cool. So the way this looks like, based on the validated pin-down flow, is that auto triage is doing its own ML model, using its own ML model to bucketize the error messages. Pin-down will take the fastest test in each bucket and identify and validate which was the bad commit. Semantic diff then can take the signals from this validated bug report and say, let's trace these signals, send them to Wayminer for analysis between passing and failing waveforms, and then Wayminer can come and say, okay, it's all due to this state machine being stuck in the failing waveforms. So that's how it looked. That was my quick update, what happened the last 2 years and how we've integrated into the Cadence flow, and all is fast and dandy thanks to the A, bug prediction, and B, validation, which builds the foundation when we can build all these tools upon it. Okay, now I'm done, Mike.
Okay, thank you very much. Thank you very much for finishing on time as well, Daniel. We got time for just one question probably. So the first question is this language specific, just Verilog, or does it do it for C, VHDL, for example?
Any language. Pin-down can handle any language, because it's just basically for pin-down, everything is text files under revision control, and it tries to back out the right combination to make the tests passing again. But semantic diff and Wayminer, which I showed here at the end, which they understand Verilog and Verilog. They are limited to those languages.
Okay, and this may be an interesting question. Is does this more apply to later stage data stage check-ins, or does it apply throughout the development cycle?
I mean, I would say that you can turn it on when you turn on regression testing. Then you can turn on this tool. This is a tool that should be integrated as part of your regression testing. So when you decide now is the time to do regression testing, which is normally fairly early in the project, then pin-down should be enabled at the same time.
Okay. Okay. So I think we can finish there. So thank you very much for Daniel. Congratulations on your integration into Cadence.
Thank you.
I trust you're enjoying it. Thank you.
Yeah.
Okay, and again, thank you for the update on pin-down.
Thank you.
Do you want to switch? Thanks, Daniel. Oh, your clap as well. Okay, thank you. Do you want to switch back to me, please, Disha?
Yeah, sure.
I'll share. Okay. Okay, so thank you for participating today. I hope you found the talks useful and interesting. If you did ask a question, it wasn't answered, we will email that question to the speaker and try and get you a feedback. Thank you to our sponsors, Ignitis, Cadence, Imperas, Brecker, Synopsys. We also thank ARM and ST for offering locations when we go back to location-based. We are still remaining all virtual. And thank you to Tessov, who helped pull this event together. The presentations will be sent out. We first of all put up the slides, and then we put up the recordings, and they're all available on the DV Club page. And if you've got any ideas, remember this talk came from my suggestions. We put those ideas together, and we do listen to you and put on talks accordingly. And we have one more talk this year, which is in November, auto-generation of a verification infrastructure for IP to SoC level. Okay, thank you very much, and we'll see you in November. Thank you.
Thank you, everyone.
Thank you, everybody. Bye-bye.
Bye.
And thank you to our speakers as well, Raj and Daniel. Thank you.
Thank you.